Okay, on to the last problem. And what most of this problem is trying to test is what are you seeing in these memory locations, and can you interpret the bit values into what the board is actually doing, like what this peripheral is doing. And so this is for analog to digital conversion. We're going to be looking at the AD control register 80CR. And so we're just trying to figure out what's happening here, what's going on in the hardware. So the first thing I'm going to do is just kind of write down and map out what these bits mean. So we can see bits 0 through 7 are cell. And hopefully we know from the labs and from working with this and or from reading, we know that that's the channels that are being converted. And it's bit 0 is channel 0, bit 1 is channel 1, bit 2 is channel 2, bit 3 is channel 3, bit 4 is channel 4. So we can already answer the first question up here, which is the channels that are being converted are 3, 4, because those two are set to 1, and that's all the first question is asking for. However, let's continue on marking this up. So bits 8 through 15 are CLK div, and that's an integer that it's written out in binary, but we're going to convert it to an integer that is dividing the clock further than what PCLK is doing. Bit 16 here is burst, so it is on. That means we are in burst mode. We are not software controlled. Bits 17 to 20, we can kind of just cross those out because they are unused, they're reserved. Bit 21 is PDN. That is the ADC's specific power bit. So we turn it on globally in PCON-P, and then we turn it on again here in PDN. So it's sort of double gated for power. And then we have bits 22 and 23 are reserved. We don't do anything with those. Likewise, bits 31 to 28 are reserved. Bit 27 is edge. It is not on, so that means it's not using that. And then bits 25 through 24, these are start. And we know that from the way that this works that we don't set those if we're using burst mode. So that would be for software controlled analog to digital conversion. So we're not going to use those because we've set bit 1 set bit 16 to 1, which is burst mode. We don't use these bits whenever that's on. So what mode is used for conversion? Well, it's burst mode, right? We saw that the burst bit is set to 1, and so that's just following that setup up here, and that's all we're doing. Okay, next up is the ADC has finished converting a sample on P1.30 and triggers an interrupt. A voltmeter reading from the analog source attached to P1.30 measured 2.15 volts. Fill in the contents of AD0DR4. Assume that no overrun has occurred and that all reserve bits can be filled in with a 0. Okay, so this is asking us to think about what a data register looks like. And so let's go ahead and scroll down to what the data registers look like. AD0DR4 is one of these, so 80 data registers, AD0 DR0 to AD0DR7, AD0DR4 is one of those, is going to have these bits. So I'm just going to go ahead to start and fill in the reserve bits because it's asking me to do that. So 0, 0, 0, 0. We're going to skip over those for now. And then from 15 or for 16 up to bit 29, we can fill in with zeros as well. So those are just all the reserve bits that we have here. We're not doing anything with those. And then we'll fill in the rest based on the problem. So it has finished converting a sample, and we're assuming that no overrun has occurred. So no overrun has occurred. That helps us do the overrun bit, so that's a 0. If no overrun has occurred, it's going to be a 0. And finished converting, hopefully that's clear that that means that it is done, and so the done bit is going to be a 1. Last part that we have to do is the result. So the result is the hard part here. We have measured 2.15 volts. And that is 2.15 volts out of a maximum of 3.3 volts. Okay? So that's what we read 2.15 on our converter, and we are, at maximum, we could measure a 3.3 volt value. So that is basically telling us what percentage of this are we seeing. And that gives us about 0.6515 is what we're seeing there. That fraction of the full value range. We're going to convert that into one of the potential values that we can see on the analog to digital converter. And we have between 0 and 4095. This is a 12-bit value here. So we're trying to figure out which one of those values is what we're seeing on here. And that is mostly going to be just multiplying this fractional value that we got by 4096. So by 2 to the 12. And so if we multiply by 4096, because our values are between 0 and 4095, this is going to be an approximation. We get to 2668 or 2669. I think I accepted both of those as possible answers because we are rounding here, and that's sort of a little too technical to know like which one the ADC is going to pick when you're in between. But we get 2668. And now we have to convert that into a binary value, so 2668 in binary, and we can just use our handy dandy Google converter, 2668 in binary, find out what that is, and that's going to be, it's a little off screen, sorry for that, but it's going to be 0011, 0110. And 0101. And that is it. So we're just converting that into binary, putting that into the bits there, and that's all we have to do for that particular problem. Okay, we're going to give this one another go because I made too many mistakes working through this last set of problems. So what is the clock speed of the ADC after all clock divisions have been applied? So we already know one of the divisions that's going to happen, which is the CLK div right here. And we'll need to look at what that means in a second. We are also going to apply the p clock select, which if we look at the table here, table 40, we can see that bits 24 and 25 are the peripheral clock selection for the ADC. If we go to table 42, that shows us what those values mean, and we can see that the 1, 1 in those bits means that this is clock divided by 8. So this is ADC, and we're going to do clock divided by 8. So we're going to take that 100 megahertz clock that we have on the LPC, we're going to divide it by 8. This is the p clock select is what we're applying here. That's going to give us 12.5 megahertz that we have left. Now we're going to apply clock div. So let's go ahead and go back to the ADC portion of the manual and just see what that looks like. So if we look here, we see that the APB clock, p clock ADC 0, is divided by this value plus 1 to produce the clock for the AD converter. So we don't want to divide by 0, right? So if this is all zeros, we want to divide by 0 plus 1 or 1 to keep the value the same. That means that we're dividing by what we have in this, which is 001 in binary, which would be 4 in decimal. So we're dividing further by 4 plus 1 for the clock div. And so that gives us 2.5 megahertz as our answer for this part. So 2.5 megahertz once we've applied all of those clock divisions. Now for part E, what is the maximum frequency of input sine waves to the selected channels that will not cause aliasing? So we're dealing with the Nyquist rate here, and that is that our FS, our frequency sampling, our sampling frequency, it has to be greater than 2 F max. So F max is the frequency in the waves that we're looking at. So that's what this question is asking us to deal with, is the Nyquist frequency, or the Nyquist rate. So we have our sort of max frequency that we can run this at. We do have to deal with the fact that we actually run at 2.5 megahertz divided by 65 cycles, right? It takes 65 cycles to do an analog to digital conversion, and so we have to divide that out first, which is going to give us the 38,462 hertz that you'll see on the solution. So 38,462 hertz is factoring in that 65 cycles. The next thing we have to deal with is selected channels. So because we are in burst mode, what we do is we constantly convert on the 2 channels that we're converting on. So we're actually going to divide this by 2 channels, and that's going to tell us the max frequency that we have for both of these 2 things. And so that's going to be 38,462 divided by 2, is what we're going to get there. And so that's going to be our sort of frequency, our sampling frequency for the two channels is this 19231. So 19231 hertz is our FS, right? And so now we need to know how fast can we actually be. So our F max is going to be less than 19231 hertz divided by 2, and that's going to be equal to this final value we see on the solution, which is 9615 hertz. So we have a fairly small value that we can get to once we've applied all of these divisions, right? And that's just because we have the clock div that's going to lower this. We have the p clock select, which is going to lower it to 2.5. And then we have the number of cycles that we're going to use. We have the number of channels that we're doing this on. And then we have finally the Nyquist rate, which is dividing it by 2, one more step. So our max frequency has to be less than 9615. So this would be a reasonable sampling rate for something like, voice, where we're not going to go over probably, 4 kilohertz or so. Right now we're at 9.6 kilohertz maximum. And so this seems reasonable for a problem like that. And again, sorry for having to take 2 attempts to do this, but hopefully this was helpful.